Introducing the Copter V3 by UAV Forge at the University of California, Irvine. Copter V3.0 has been specifically designed by our team of undergraduate experts for stable flight and efficient performance. The drone is a single-body, free-flying aircraft with a takeoff weight of 13.5 kilograms and is fully capable of autonomous flight. It is upgraded with customized software for advanced obstacle avoidance, dynamic path planning, drop target detection, as well as full return to land and autonomous flight termination capabilities. Jose Callejas is a second-year electrical engineering major. He is the team's competition chief and a member of the avionics subteam. Bogdan Kovtun is a third-year aerospace engineering major and the aircraft subteam lead. Vince Chen is a fourth-year computer science major. He is the team's safety pilot and a member of the navigation subteam. Dirk Fan, a fourth-year mechanical engineering major and the lead of the navigation subteam. Jingqi Xia is a third-year aerospace engineering major and a member of the aircraft subteam. Changhao Young is a third-year computer engineering major and a member of the avionics team. Eric Bradley is a second-year computer science major. He is the team's ground control station operator and a member of the imaging subteam. Ozzy Sanchez Saldana is a second-year mechanical engineering major and a member of the payload subsystem. Copter V3.0's carbon fiber airframe has 3 layers of plates for maximum support and efficient placement of electronics. Attached to the plates are 4 carbon fiber arms that support and stabilize the AP-50-16 Hacker motors, and 2 carbon fiber legs for safe and secure landings. The frame was designed to be lightweight for quick maneuverability while sturdy enough to support the payload docking mechanisms. The Aeris M900 frame, in conjunction with the selected motors and electronics, provides a high thrust-to-weight ratio while providing the structural integrity necessary to support 5 kilograms of payload on its undercarriage. The team ran simulations on common aircraft styles and found the rotary wing style was better suited than a fixed wing design for optimal completion of this year's mission requirements. The drone is equipped with 20-inch high-pitch carbon fiber propellers to increase RPM and the speed of the drone for fast completion of the entire course. Calculations determined that the weight ratio of the payload to the aircraft was best handled by a quadcopter frame for carrying the payload over 12 miles. Dropping the payload is more accurate from a stationary hovering aircraft with rotary wing design rather than having a moving fixed wing. The aircraft team used online software to simulate the aerodynamic forces acting on several different styles of quadcopter bodies. The Aeris M900 airframe was found to be the most efficient given its low cross-sectional area and thin, sleek frame parts. The software eCalc was used to calculate the best combination of motor types and electronic motor controlling devices, as well as the batteries required to complete the long distance required. The full payload delivery system consists of individual servo-operated drop mechanisms for each payload bottle. All 5 mechanisms are arranged in a circular pattern, equally distanced and attached to a large bracket. This bracket is attached to the bottom of the quadcopter's chassis via 3D printed mounted plate. Each mechanism includes a housing space for an MG90's servo motor with a servo arm. The servo arm rotates into and out of a small shaft above the top of the servo motor, which releases the rectangular rod that supports the payload when the payload needs to be dropped. The rectangular rod is specifically designed with an extruded head at the top and a long curved arm at the bottom to minimize the amount of torque acting on the servo motor and maintain a tight center of gravity for the entire payload system. Velcro straps looped through the curved arms secure the payload bottle. Each bottle has a set of 2 wide rings with 8 loops each, where a paracord is threaded through and attached to the parachutes. This design puts the payload bottle's center of gravity in line with the extruded head, which also minimizes torque acting on the servo motor. Several alternatives were considered in the design process of the payload drop mechanism. The first iteration consisted of a single large cage incorporating a revolving mechanism with 2 plates that each had 1 hole. The large cage was designed to carry all 5 payload bottles and drop them all individually for their specific targets. The advantage of this design prevents delays caused by the calling of the quadcopter back for restocking, which decreases overall course completed time. However, the cage design created increased difficulties with manufacturing and surpassed the project's designated mass threshold of 300 grams. This design was abandoned in favor for the current less intrusive containment system with minimized power consumption. The motors of this new model have been thoroughly tested for stall torque, and the model is lightweight at 11 grams overall. Powering the electronics of the drone are 2 25,000 mAh lithium polymer batteries. The batteries supply 4 120 amp ESCs, 4 235 kilovolt motors, and the onboard computer, the Jetson Xavier. The Xavier is equipped with a powerful built-in GPU for improved processing time of imaging neural networks and built-in GPIO pins for payload servo activation. The drone is equipped with Pixhawk 4. Attached to the Pixhawk is the Pixhawk Cube 2 Black Flight controller, which supports PX4 autopilot firmware, the Hero 3 GPS with U-Block high-precision GNSS modules, and the RFD 900X radio modem for communication with QG ground control are also connected. Before takeoff, we initialize the ODCL and the navigation pipeline on the onboard computer via SSH Wi-Fi connection between the Jetson Xavier and the ground station. When the drone takes off, the Wi-Fi connection is lost due to range, but the pipelines continue running on the onboard computer. During and after takeoff, there are two main communication channels active throughout a flight. First, two RFD 900 US telemetry radios are used for all communications between the ground station and the quadcopter's flight controller. Second, we have wired USB connections between the Jetson Xavier and the flight controller. All onboard components use the Mavlink communications protocol for UAVs for commands and telemetry data. Our quadcopter runs PX4's quadcopter firmware on the Pixhawk 4. The firmware has separate PID controllers for position, velocity, and orientation. PX4 has a feature that performs sensor fusion between redundant IMU and magnetometer data, which is passed through an extended Kalman filter. This reduces sensor noise, bias, and drift to provide an accurate assessment of the state of the drone. The system additionally utilizes RTK GPS to achieve 1 centimeter positional accuracy in real time. The RTK system cross-references a pair of GPS devices, one on the drone itself and another on the ground station, to increase positional accuracy. Safety features on the PX4 autopilot include manual mode switching on takeoff, and the ability to interrupt the script and regain manual control at any point in the flight. The competition tasks, including boundary, waypoints, and drop zone, are entered in a JSON file, then read, processed, and ordered appropriately through a Python script. This script continuously reads for an obstacle avoidance waypoints, drop waypoints, or the next waypoint, updating the order of traversal appropriately. The waypoints are then sent to the flight controller using a network of Mavros topics, so the appropriate Mavlink commands may be processed by the PX4 firmware to steer the drone in the appropriate waypoints. PX4 provides a robust built-in obstacle avoidance solution, but the drone's flight speed will be capped at 3 meters per second. Consequently, our quadcopter utilizes a custom geometric obstacle avoidance algorithm, prioritizing computational speed over precision. Our algorithm uses data from the Intel RealSense stereo camera. We chose this camera for its 20-meter range and its ability to provide 3D data. We're essentially looking for a safe path within the camera's 86-degree field of view, where the bounding volumes of objects don't interfere with the safety distance around the drone. First, we filter objects past certain height limits to decrease the data points. Remaining objects are approximated through cylindrical volume estimation. This allows us to consider the objects as circles in the XY plane in our simplified algorithm. The algorithm then checks for any intersections between the bounding circles and a predefined limit around the projected path. If the current path is found to be unsafe, the algorithm radially sweeps the 86-degree field of view to find an alternate path. If no safe paths can be found, we turn the drone 45 degrees and repeat the process. Once a safe path is found, the compass heading is used to calculate a new waypoint for obstacle avoidance. The drone is equipped with the GoPro Hero 10 for built-in image stabilization, allowing us to capture 5.3K resolution images which are unaffected by local vibration of the motors. The GoPro's field of view is also large enough to capture the entire width of the drop zone. Our ODCL system for drop target detection starts by fragmenting the 5.3K image into tiles, then runs an instant segmentation model trained on synthetic data on each of the tiles. The detections are ultimately stitched together using non-max suppression. After additional segmentation to distinguish letters from shape, we use a convolutional neural network to classify the letters. The images are then sorted by similarity to the given list of targets. The pixel coordinates of each detected target are then mapped to real-world coordinates. The best guess location for each target is continually updated based on new data. Safety is given the highest priority for our team. Prior to beginning work in lab, all team members completed lab safety training to ensure safe and proper use of lab equipment and PPE. While working in the lab, the team always conducted work in pairs, maintained a comprehensive FOD program, and strictly enforced the use of PPE and safe operating procedures. To reduce the risk of FOD, increase safety, and prevent component malfunction, all fasteners on the drone were installed with a thread locking adhesive Loctite. All electrical work was conducted while power sources were off and removed from the system. During full operation drone testing, a safety officer was assigned to monitor all proceedings. A minimum distance of 50 feet was enforced when the rotors of the drone were active, and return to home and manual override capabilities were in place to ensure an operator could regain control of the drone in the event that the drone engaged in unsafe maneuvers.